In Lesson 4 of Module 2, the effects of irradiation on metals, we'll start to take an in-depth look at what happens when these very high energy fast neutrons collide with the crystalline lattice of metals. And we're going to start at the atomic level for this. We're going to look at radiation in the nuclear reactor. We're going to talk about the irradiation event when this neutron strikes the atoms in the structure of the metal. We're going to look at damage at the atomic level, and we're going to start to look at mechanical effects from this irradiation. We'll look at the effects on phase transformations, which can be very serious. And so we have a number of goals here. We're going to make clear the effects of irradiation. We're going to do that starting at the atomic level. That's where you really have to start to understand what's going on. We're going to understand the segregation that results from the atomic level displacements that occur when a high energy neutron strikes atoms in the lattice. We're going to understand the nucleation and growth of voids and the implication of this on the properties of the metal and the structure of the metal. We're going to look at phase changes and make these clear because there are phase changes that occur because of this irradiation, and we're going to look at the implications of this on both corrosion and mechanical properties as we go through these lessons. We're going to delineate the changes in mechanical properties that occur from irradiation, and they are not insignificant. They're something we have to understand pretty thoroughly. The sessions in this lesson, and there are a number of them, it becomes a fairly long lesson. It'll be a hard thing to view all at one sitting. So we have a number of sessions. Session 1 is one we're in right now, is the radiation damage process, step by step. Session 2 is the interactions between ions and atoms. Session 3 is the displacement of atoms. Session 4 is radiation-induced segregation, which is important in alloys, which are generally what we're talking about in real life. We're going to look at the nucleation and growth of voids. Then we'll talk more about irradiation-induced phase changes. And we'll end up looking at mechanical effects caused by irradiation in Session 7. And unless you'll see otherwise noted, the figures and the equations come from our textbook, Materials Fundamentals of Radiation Material Science. And that text, as I mentioned earlier, goes into a lot greater depth than we will. We're going to take the highlights. We're going to look at some of the mathematics involved. We're not going to try to dig into that too deeply. It's beyond what we need to do for this course. It's there. If you like to read through it and try to understand all that, the text is very good at explaining it and going through the implications of this, but the math is pretty advanced. So let's look in Session 1 at the radiation damage process step by step. We have an interaction of a very energetic incident particle, starting off with this high energy, high speed neutron, which is very small, and its interaction with the lattice, the crystalline lattice of the metal and the atoms that are in that lattice. And what happens is we transfer kinetic energy to the atom from the high-speed neutron. These are 1 to 1.5 MeV, very high energy neutrons. And what that causes is the knock-on of an atom. If that neutron strikes the nucleus of an atom, it will knock it out of its position. We call that a primary knock-on atom, pKa. So try to memorize that term, primary knock-on atom, pKa. It's the initial atom that's knocked out of its lattice structure. It may gain so much energy that it will knock other atoms from the structure. And we'll be looking at the time scale of this as well. And this is basically the displacement of a lattice ion from its normal lattice position. Now, in materials at temperatures above absolute zero, there are missing atoms, voids, in the structure where an atom is missing, and there are interstitials where that atom goes. That occurs just from thermal energy alone. But here we're talking about a much higher incidence of actually knocking atoms free of their normal structure. And when that pKa, that primary knock-on atom, the first atom that gets knocked out by any given neutron, we then can generate additional knock-on atoms because the atoms will strike others with high energy until finally that energy gets dissipated. And remember, we've got a very large number of neutrons striking the metals in our reactor at any given time. So we're going to look at just one event, this cascade, if you will, of what goes on from each neutron that strikes the structure. So we end up then with what we call a displacement cascade. We end up then knocking atoms free. We have lots of neutrons striking the structure, so we get lots of primary knock-on atoms and atoms that are secondary. And we end up then producing voids or missing atoms in the crystalline structure, along with interstitial atoms that have been knocked free. So the termination of a pKa is an interstitial. Let's first of all look at some of the atomic particles we're talking about. It's important to get a feel for their size and the structure of the atom and the mass. So the neutron has a mass of 1.6749 times 10 to the minus 24th grams. You aren't going to weigh that on your kitchen scale easily. There is no charge, it's neutral, and it is produced in the nuclear process by the decay or the fission of a uranium-235 nucleus. So when we get a fission event, when a thermal neutron is absorbed by the nucleus of a uranium-235 atom, it creates uranium-236, which is unstable. It fissions into two large fragments and releases 2 to 3 additional high-energy neutrons and a bunch of energy, which is, of course, what we're looking for, is that atomic energy. The proton has basically almost the same mass. It is 1.6726 times 10 to the minus 24th grams, but it has a positive charge. An alpha particle is essentially an helium nucleus that's been stripped of electrons, 2 protons and 2 neutrons. Something that we worry about more in space, but not so much in this environment, and has a mass of 6.64 times 10 to the minus 24th grams. So it's the mass of 2 protons and 2 neutrons. The electron has much, much lower mass, 9.1 times 10 to the minus 28th grams. So that's very low mass, almost 3 orders of magnitude, almost 4 orders, is more than 3 orders of magnitude, compared to the neutron or the alpha particle or any of the ions that we will be discussing in our structures. And it has a negative charge. So that's what we have to consider in size, in masses of these materials and their charge. We have to consider both. We also have ions and atoms that we have to consider from the metal itself. So let's look at size comparisons. I think this is kind of important to get a feel for what's happening when these very small neutrons enter the lattice, crystalline lattice of a metal alloy. The neutron or the proton basically have the same size, 1.75 times 10 to the 6th nanometers, or 1.75 times 10 to the minus 15th meters. That's really small. The diameter of the nucleus of a hydrogen atom, the simplest atom, which is one proton surrounded by an electron, is 1.75 times 10 to the minus 6 nanometers. That's the diameter of the nucleus, because it is a proton. That's the diameter of the nucleus of the hydrogen atom, 10 to the minus 6 nanometers. The nucleus of a uranium atom is 15 times 10 to the 6 nanometers. It has 235 protons and neutrons, or 238, depending on the isotope, crammed into a ball, and it has a diameter of 15 times 10 to the minus 6 nanometers. So the nucleus of a uranium atom is obviously much larger. than that of the hydrogen atom, but it is still very, very small. The hydrogen atom has a diameter of 0.4 nanometers. That's a lot different than 1.75 times 10 to the minus 6th nanometers for the nucleus of the hydrogen atom. So there's a huge difference between the size of the nucleus and the size of the atom itself. Just an enormous difference. We're talking 6 orders of magnitude or more. The iron atom is 0.25 nanometers in diameter. The uranium atom is 0.28 nanometers in diameter. So basically, the hydrogen atom itself is actually larger than an iron atom or uranium atom. I am sort of a hands-on person. I have to try to put things like this into perspective. And to me, to try to visualize this extraordinarily tiny neutron striking an extraordinarily tiny but much larger atom is a little bit difficult. So what I've done is try to picture this as calling the neutrons a BB. I can picture a BB being shot at very high velocity. So if we have a very high-powered BB gun, and if it shoots standard BBs, which are 4.57 millimeters in diameter, and if we picture those BBs as the neutrons we're shooting in a reactor at the metals that make up the reactor, we're looking at the radius of the BB divided by the radius of the neutron to give a ratio of a BB compared to an actual neutron of 2.61 times 10 to the 12th. So we got 12 orders of magnitude larger, or the BB is larger than a neutron. And we can picture what a BB looks like. If we're shooting these BBs at an iron atom, as in steel or stainless steel, the iron atom, is on the same scale as the BB, 6.53 times 10 to the second meters in size, or about a little over 2,000 feet in diameter. So we're shooting BBs at an atom which is a sphere 2,000 feet in diameter. So we have this huge sphere that makes up the iron atom that's 2,000 feet in diameter. Picture that. We're shooting BBs at it at very high velocity, and the nucleus of this iron atom is only an inch in diameter. So we have this very large sphere, 2,000 feet in diameter, with a 1-inch nucleus at its center. And we have to hit the nucleus with the BB in order to cause an interaction. And in the case of a uranium atom, the nucleus is roughly that same size. So when a thermal neutron is trying to strike a uranium-235 atom nucleus, you've got a 1-inch ball sitting in the middle of a 2,000-foot diameter sphere, and you got to hit that. So we're going to talk now about the interactions of this little BB with a 2,000-foot ball, or a neutron with an atom that has a very tiny nucleus. So the nucleus of any atom is extraordinarily small, 1 inch in a 2,000-foot ball. So that's the scale I want you to keep in your mind. So a U-235 nucleus is about 39 millimeters in diameter. It's larger. It's a heavier element. So we're shooting BBs at super blimps. The Goodyear blimp, as a matter of fact, if you've ever seen one of the blimps flying over a sporting event, is 192 feet long, 60 feet tall, 50 feet wide. The Pyramid of Cheops is 460 feet tall. Tallest buildings in the world, including the towers on top, are in this 2,000-foot range. Most of them are 1,100 feet. So we're really talking about shooting BBs at some pretty large spheres. I hope that's a perspective that will be useful to you when we start talking now about these neutrons entering a metal lattice, because it has to actually hit or come close to hitting the nucleus for there to be any interaction and driving this atom free. So we have here the crystal structure of iron, body-centered cubic. We have iron atom at the center. We have iron atoms at the corners of a cube. The atoms are touching across the diagonal of the cube. They're actually in physical contact. They're not in contact on the edges of the cube or across the center of the face of the cube. They're in contact across the diagonal of this cubic structure. So the iron atom is 653 meters in diameter, and its nucleus is 25 millimeters, about an inch in diameter. Just to picture that. So the BB we are shooting in the unit cell is this big. You see it down here? Well, of course not. You can't picture it here. It's 0.000033 times as big as the diameter of the length of the edge of the cell. So on this scale, you just can't see it on the screen. So we're just, really picturing some very small things striking this structure here. Let's look at some typical particle energy levels. The fast neutrons are 1.5 MeV from the fission event, 1 to 1.5 MeV. The moderated or slow neutrons, which are more easily absorbed by the nucleus, if it's struck, of uranium-235, have an energy of 0.025 eV, not MeV. And it takes about 18 scattering events with hydrogen nuclei in light water reactors to slow this very high speed, high energy neutron down to becoming a slow neutron. And we, of course, have neutrons everywhere in between these values as they are going through the water in our light water reactor. So in a light water reactor with just plain water, it takes about 18 scattering events. In other words, neutrons have to actually hit the nucleus of hydrogen atom, about various atoms, about 18 times to slow it down to this thermal level, which is what is easily absorbed by the uranium nucleus. And EV is equal to the amount of kinetic energy gained by a single unbound electron when it accelerates through an electric gradient potential of 1 volt. So 1 electron volt is equal to 1.6 times 10 to the minus 19th joules. 1 MeV is thus equal to 1.6021 times 10 to the minus 13th joule, just to give you a feel for what these energies are. 200 MeV is the energy released typically in the fission of one U-235 nucleus on average, and it depends on how the atom actually breaks up. It can have different fragments, different isotopes of slightly different size and different elements when it splits. It's not always the same elements that are formed. But the average energy is 200 MeV of energy released in one fission reaction. So we're talking about some very high energy levels that are available to us and that's of course the attraction of using nuclear fission as a source of electric power. We're going to look now at or start to look at least, at the damage event itself. And this can get very complicated, and the math behind it involving some quantum physics is very deep, and we're gonna touch upon that. We're not going to go into great depth because we're more interested in the practical effects of this on our materials and how they are degraded by radiation. The simplest model is that we have a hard sphere with enough energy to knock an atom out of its lattice site. So the simplistic vision is of a large billiard ball, very large billiard ball, being struck by BBs, and if we strike the nucleus with enough energy, we might be able to knock it free. So we have this hard sphere model of the structure of atoms in a lattice. So what we need to have as a goal is to be able to describe the energy-dependent flux of the incident particle, a neutron in our case, and the energy transfer cross sections, or the probabilities for collisions between atoms. And then if we can do that, if we can get this probability, the energy transfer cross section, we can quantify the production of these pKa's, the primary knock-on atoms, and then the secondary ones, in a differential energy range, and then utilize that to determine the number of displaced atoms. So the goal is pretty simple. Actually explaining what happens from a physics standpoint is not so simple, and certainly the math is not simple. So we're going to look at some of that. I just want you to be aware that these treatments exist. If you're interested, you can dig into it. We're not going to spend a lot of time on this. First of all, let's look at the time scale for the formation of these point defects as it occurs. This is the approximate time scale for the production of defects in metals that have been irradiated by high energy neutrons. This is the time after a neutron strikes an incident strikes an atom, and this is the event that occurs, and this is the result. So the first thing is that we have this high energy neutron at 10 to the minus 18 seconds energy transfer to the incident particle. It takes 10 to the minus 18 seconds for this energy transfer to occur, and resulting in the creation of a primary knock-on atom. In 10 to the minus 13 seconds, we will have a displacement of lattice atoms by the pKa. So we knock, in a very short period of time, we knock an atom free. And it may have very high energy itself from the incident neutron. And that atom can strike other atoms and displace them from the lattice, creating then a secondary knock-on atom. And so we have started then in 10 to the minus 13 seconds this displacement cascade. In 10 to the minus 11th seconds, order of magnitude 2, we have dissipation of the energy of this primary neutron and the primary knock-on atom. And we end up then, we start getting dissipation of energy. We start at that point, we no longer have fast-moving atoms in the structure. We start to get spontaneous recombination and clustering. So we're going to look at what happens on this time scale. We start now to have these interstitial atoms that have been knocked free, falling back into the voids that are left behind, the vacancies that are left behind when we knock an atom out of its spot. So we have we end up with stable Frankel pairs as a single interstitial atom and a vacancy, and clusters of defects. So we're going to look at how these form. We're going to look at some computer simulations toward the end of this whole system. In 10 to the minus 8 seconds and greater, we have defect reactions by thermal migration. The vacancies and interstitials start to meld together with each other, and we start to heal the structure. So we have these single interstitial atoms and vacancies recombining with each other. We get clustering, we get trapping, we get defect emission. And this is over a longer time scale. But you'll see these time scales are very, very short. So it doesn't take long when a neutron enters a metal for there to be the creation of a primary knock-on atom. And that's the time scale we'll be looking at. The neutron itself is charge neutral. So the interaction of the neutron striking an atom is relatively straightforward. And basically, the elastic collisions that occur can be viewed as hard sphere collisions. And this is when a neutron, high energy, hits the nucleus of the material, of the atom. Basically, once you create a primary knock-on atom, now you've got interactions between atoms or ions of the metal that's struck. But in a metal, we'll just picture it as being atoms. We strike iron, we have iron atoms that are knocked loose, and they're going to hit other iron atoms. So once we get this primary knock-on atom, we now have interactions between atoms in the struck metal. So the initial neutron striking is a pretty straightforward event, but then we get into problems with atoms which have nuclei which are positively charged, surrounded by a large number of electrons orbiting the nucleus. And so we end up with all kinds of other factors that affect the subsequent knock-on or displacement of atoms. So now the positive charge of the nucleus and the negative charge of the electron cloud around the nucleus become important. We can't ignore them any longer. And of course, we're looking at, in many cases, a large number of atoms that are knocked loose by atoms that are knocked out of the structure. So it gets very complex once we get past this first primary knock-on atom situation. The atom-to-atom interaction is the low energy limit for an ion-atom interaction that are found in the reactor core and in accelerators that we use to study these kinds of reactions over a wide energy range. So we have a wide energy range here. It's what happens in a reactor core and also in some of the test equipment. We'll talk about that later, that we use to study these kinds of phenomena. So we can end up then with the last type of interaction, an ionization collision. Gets pretty involved here. So if we have a 1 MeV neutron that's incident on various elements, we have energy transfers that are listed below. T is the average energy transfer. And we also produce in gamma energy. 1 MeV neutron hitting carbon will produce a transfer of about 0.14 MeV to the carbon. 1 MeV neutron hitting iron is going to transfer less energy, and the average energy transferred, because this is a very heavy, much heavier. And on the case of uranium, the average energy is 0.009 MeV. So we have this elastic scattering that we've just discussed. This is a neutron hitting the different elements. And we can have energy transfer by inelastic scattering, neutron and two neutron reactions, and by neutron gamma energy reactions. So the first two reactions become important above neutron energies of about 1.0 and 8.0 MeV, rather, respectively, while the earlier one occurs at the thermal neutron energies in uranium-235. So you're talking about thermal neutrons. So we're going to look at that we're going to start to look at that. And once again, I want to just tell you, we're not going to try to really dig into this too deeply. I'm going to explore it with you. I'm going to expose you to it so you can see that the study of these collisions in a metal becomes very, very complex. Basically, if we get a neutron colliding with a nucleus, and it's absorbed, it creates a compound nucleus. This can decay, and that will emit a neutron and gamma rays, a gamma ray or gamma rays, depending on what happens and what the element is. So we end up then getting this neutron gamma type of interaction. The emitted neutron is basically can be pictured as the neutron bouncing off of the nucleus, but in fact it is actually absorbed and then re-emitted, and you end up also then can result in generating some gamma energy, which is high energy radiation, and it does affect the materials in a reactor. So we have to. The primary problem is the neutrons that are generated, but gamma radiation is also something we have to be aware of. In this process, there is a loss of kinetic energy. This is not the same as the hard sphere collision process we looked at earlier, because now we're talking about some of the energy of the incoming neutron being released as gamma energy. gamma radiation. And so the neutron then does not have that leaves, it bounces off, does not have as much energy as the incoming nucleus had. So this basically results in resolved and unresolved components of the collision. If you looked at this as a hard sphere model, and it was a totally hard sphere, if the neutron bounced off the much heavier nucleus, it would carry with it basically this. It would carry with it energy. It would give up some energy to the nucleus of the atom, and those two would the energy that the neutron retained and the energy that was gained by the nucleus of the atom would equal the incoming energy of the neutron. But here now we have this unresolved component, which is gamma radiation. And the neutron can take part in additional collisions, and we can also have emission of a second neutron. So we can have either one or two neutrons released. And of course, that means taking a neutron from the nucleus of the atom. We have photon emission reactions. Basically, the energy of the recoiling nucleus is sufficient to displace the atom, so that you can actually knock the atom loose. The electrons circling, if you will, or associated with the nucleus are going to follow along with it as it's displaced. This type of photon emission reactions is important in looking at radiation damage in reactor pressure vessels, where the gamma flux that occurs is comparable to the fast neutron flux in the reactor core itself. So we get a lot of gamma radiation flux. So here we're looking at energy transfer, excuse me, and energy transfer cross sections for various types of neutron nuclear collisions. So we've got then the energy transfer. This is the mathematics of looking at this energy transfer. We're not going to go into that deeply. Over here is the equation in the textbook. You might want to look at that, print this table out, and sort of look up these equations. They're given here, and read over those sections if you're interested. This is the elastic scattering, where we have basically the hard sphere type of model. If we have scattering, the transfer energy is a much more complex study and equation, as is the energy transfer cross-section. So we have some pretty heavy math here to look at. This is an N to N type of relationship, and once again a different formula for looking at the transfer energy and the energy transfer cross-section. And this is where we have neutrons and gamma radiation involved. Now, I certainly would not want to spend time in this course looking at degradation of materials and corrosion of materials to study this in any depth, because it's really a study of physics, and we're looking for practical results. But this is the type of math that one has to look at if you really want to dig into what happens when these neutrons strike a metal lattice and knock off atoms. Session 2, we'll start looking at the interactions between ions and atoms when we knock atoms or ions, create ions from the lattice, and they accelerate through the material, looking at what interactions we'll see. We'll do that in session 2.